So we will look into equilibria or equilibrium. Okay, equilibrium happens, okay, for a reversible reaction. Okay, so we know that there are some reactions, okay, in chemistry they are going to be reversible, and once you actually have them for a certain period of time, they can actually achieve equilibrium. And in order to achieve equilibrium, they satisfy four criteria. Okay, the first criteria is going to be the reaction at equilibrium. They are still going to be dynamic. The reaction is continuously happening. They do not stop. The second is going to be the rate of forward reaction. They are the same as the rate of backward reaction. So rate of forward equals to rate of backward. And the third thing is going to be the concentration. Okay, the concentration of reactant and product at equilibrium, they are going to be constant at equilibrium. And the last one, we are assuming that equilibrium happens in a closed system, where what is closed system? There's nothing, no matter coming in, no matter going out. So nothing coming in, nothing going out. So that is closed system. So if anything goes, let's say going into the system and so on, okay, then this guy will start to come in, which is going to be Le Chatelier's principle. Okay, according to this principle, whenever the system is at equilibrium, when you disturb that equilibrium, that whatever things that you disturb, that part must be removed. Okay, so the whatever small change that you put into the system, that small change must be removed. How do you remove that? By shifting the position of the equilibrium. So LCP has stated, okay, the rule for, okay, concentration. They have stated for the rule for pressure, rule for temperature. Okay, but do remember LCP do not come in when it deals with catalyst, because catalyst is going to increase the rate of both forward and reverse reaction. Therefore, catalysts do not change the position of the equilibrium. Okay, no change in position of the equilibrium. So let me actually give you some example, okay, of how LCP, okay, can actually be used. Okay, I'll give you three examples. Okay, so the first one, we start with concentration. So let's say we have A plus B to give you C. And all of this, let's say, is going to be in aqueous. Okay, aqueous. So if I increase the concentration, okay, of C, for example, according to LCP, what I need to do, I need to bring down the concentration of C. How do I bring down the concentration of C? By making them to react to give you the A and B. So this is going to be the position of the equilibrium will be shifted to the left. Okay, so in that sense, what will happen? I am going to increase my A, I am going to increase my B, and I am going to decrease my C. So that is going to be what is going to happen according to LCP. So let's actually talk about, okay, the number two. So this is number one. Let's talk about number two, pressure. So related to pressure. So let's say I have A plus B to give you C, and assume that all these are going to be gases. Okay, so let's say I have another one, D, 2D, for example. So this is gas. Okay, this is gas. Okay, so what I need to do is, okay, the first thing, do remember, okay, the pressure is only affecting the product or the reactant that are gases. So they are all gases, so it's okay, fine. Okay, you can use all of them. But if you have a situation like, for example, A plus B to give you C plus 2D, and let's say your C is going to be solid. So what we need to do is we remove the solid. Okay, we don't want the C to be involved over there. So here, what we do here, I'm going to give you two examples here. So the first example, okay, if all of them are gas, you take the number of moles of A and B. So 1 plus 1 is 2. Take the number of moles of C and D. 1 plus 2 is going to be 3. So 2 to 3. So here, if let's say, okay, they are telling they are increasing the pressure. The system is already at equilibrium. You're increasing the pressure. So according to LCP, what you need to do, you need to decrease the pressure. How do you decrease the pressure? You decrease the pressure by moving from the higher number of moles to the less number of moles. So the position of the equilibrium is shifted to the left now to favor, okay, less molecules, okay, to favor less molecules or less particles. So in that process, what is happening? Your A, okay, will become more, your B will become more, your C will become less, your D is going to become less because they are reacting. Okay. So let's actually apply the same thing. Okay. Let's say I'm increasing the pressure over here for this example. So what happens? So first of all, you need to actually take 1 and 1, all gas. So 2, 1 plus 1. So this is solid. I'm not going to include this. Okay. This is going to be gas. So this is 2. I put 2. And you can see the number of moles are the same, 2 and 2. So when I increase the pressure, according to LCP, you're supposed to decrease the pressure. But since, okay, the number of moles of both products and reactants are the same, so there is no change in the position of equilibrium in this case. Okay. So you need to be careful with all these examples. Okay, no change in position of equilibrium. So I'm going to actually show you number 3 now. Okay, so I have showed you concentration. I have done pressure. So let's actually look at temperature. So in order to look at temperature, let's say I have A plus 2B. I give you another equation. So I have C. And let's say the delta H is going to be positive. Okay, so this is going to be an endothermic reaction. And I'll give you another example also, A plus 2B to give you C. And let's say now we are dealing with a negative exothermic. So 2 examples I'm going to discuss. So here, okay, for the first example, let's say I am actually going to increase the temperature. Okay, the system has already reached equilibrium, but now I'm increasing the temperature. What will happen? According to LCP, what I need to do, I need to bring down the temperature. So how to do that? So first put your hand over there. I taught you how to do this. Okay, so if it is plus, then it's endothermic. So it's going to be your hand will feel cold. And here, if you put your hand over here, this is going to be hot, going to be opposite. So now, when I increase the temperature, I need to bring down the temperature. How do I bring down the temperature from moving from hot to cold? So the position of the equilibrium now is moving from left to right. It's moving shifted to the right. But I told you related to temperature, okay, please say it will the position of the equilibrium will favor, okay, what reaction? This is going to the right is positive, so will favor endothermic reaction. So there is extra thing that you need to write. Okay, it will favor endothermic reaction. In that process, your concentration of A will decrease, your concentration of B will decrease, and your concentration of C will actually increase because it's being formed. Okay, so this is one example. Let's actually have a look at the second example. Okay, if let's say now I'm actually increasing the temperature for this. Okay, so what happened? Yeah, so here, okay, the same thing. You put the hand over here, your hand, and this is negative, so this is going to be hot. So you put another hand over here, this is going to be cold. So when you increase the temperature, you need to bring the temperature down. How do you bring the temperature down? By moving from hot to become cold. So the position is shifted to the left. But I will write it down as it will favor, the position of the equilibrium will be favoring. This is negative, this is positive. It means this is endothermic. Okay. So will favor endothermic reaction. Okay. The position of the equilibrium will be shifted to the left to favor endothermic reaction. In that process, what will happen? My concentration of A will increase, my concentration of B will increase, my concentration of C will decrease. Okay, so this one is done. So talking about catalyst, I think I already told you there is no change in position of equilibrium. So let's actually move on to the Kc and Kp part. Okay, so Kc and Kp, they are called equilibrium constant. Kc is going to be more suitable to measure for aqueous. It can be also used for gas. We will not include solid, do remember. Okay, so solid, the concentration is constant. We are not going to include solid. but for Kp is only for gas. Please take note. Okay, only for gas. So let's say if I'm dealing with A plus 2B, okay, to give you C, and all of these are going to be gas, okay, gas and gas. I can express this using Kc. How do I express using Kc? Kc is going to be concentration of C divided by concentration of A, and then concentration of B to the power of 2. Okay, so this is how I express that. Okay, that is concentration. So product divided by reactant to the power of the stoichiometric values over there. Okay, the ratio. So if I want to represent this same equation in involving Kp, so they are all in gases, I will write down as partial pressure of C to the power of 1, okay, divided by partial pressure of A, okay, times the partial pressure of B to the power of 2. So do remember, okay, you can express them using these things. And in this case, to calculate partial pressure of anything, C or something, the number of moles of C divided by total number of moles in the system, you times with total pressure. Then that will give you, okay, the partial pressure. So we have done these examples. Okay, so do remember, if I put them, tie them together, okay, Kc and Kp, okay, they are not affected, okay, they are not affected by pressure. Pressure increase or decrease, Kp and Kc do not change. Concentration increase or decrease, Kc and Kp, they do not change. Okay, whenever it involves catalyst, okay, no change as well. But involving temperature, okay, your temperature will affect Kc and Kp. Your equilibrium constant is only affected by temperature. So this is something that you need to actually take note as well. Okay, Kp and Kc. And of course, okay, in this part, how to calculate and so on, do not forget how to use ice. Okay, for example, A plus 2B to give you C. And let's say all of them are aqueous, aqueous, aqueous. Let's say ice. How to apply ice? I stands for I is initial, C for change, E for equilibrium. So let's say in at initial you have 1 mole and 1 mole of B. Okay, and then at you need to actually understand at equilibrium, at initial, when you have 1 mole and 1 mole, of course there is no product, so automatically there is going to be 0. And let's say in the question itself, they say at equilibrium, you let it to react, and at equilibrium, suddenly you found out that this is going to be 0.05 moles, okay? And all this in 1 dm cube, for example, okay? Then they say you found out that they have 0.05 moles over there. So what we need to calculate, so I'm using the pink ink over here. So we need to know that from 0, how did you get 0.05? So the C, the change is going to be plus 0.05. So in order to do this, okay, do remember your change is affected by the stoichiometric equation. A, in front of A is 1, 2, 1. So 1 represents 0.05. So this one, okay, they must actually the same, 0.05. How about here, 2? So here will be 2 times 0.05. So 0.1. But do remember, for product, you are forming, so it's plus. Okay. But for reactants, you are reacting, so minus and minus. So what happens at equilibrium? You just use these two. 1 minus 0.05, you will get 0.95. 1 minus 0.1, so it's going to be 0.9. And all this information is the one that is required for you to write the Kc. So when I write the Kc, okay, Kc equals to, okay, it's going to be, if I put it as an expression, okay, it's the concentration of C divided by concentration of A divided by concentration of B to the power of 2. So when I put it in, please remember this thing. Very, very important. You are calculating the number of moles. You need to still show it's going to be concentration because they have mentioned it's 1. Even though it's 1, you write it down. Yeah. For C, it's going to be 0.05 divided by 1. number of moles divided by volume. That's going to be your concentration of C. Divided by A. A is 0.95 and then divide by 1 bracket. And then the concentration of B is going to be 0.9 divided by 1 to the power of 2. And then you calculate and give your answer. Okay, but the units are going to be always different. Okay, so this one you need to take note as well. The units, okay, this is going to be concentration as mole per dm cube. And then you can see divided by 1 and 2. So mole dm negative 3 to the power of 3. You can cancel and cancel. Okay, so you will write down the unit will be 1 over mole per dm negative 3 to the bracket of 2. So it will become mole negative 2 dm 6. Okay, so this is another skill that you need to actually remember. Okay, so all these calculations and so on, okay, please remember this. Okay, and I have mentioned also related to ice, like for example, if you have A plus 2B to give you C and D, if the number of moles are the same, okay, the number of moles are the same. So when we actually apply ice, okay, please remember at equilibrium, most likely whatever number, not most likely, all the time, okay, all the time, you will have the same value of this C and D. If your, okay, your number of moles over here, they are the same. So you can actually just put X and X. They are going to be the same. So sometimes they have, they can ask you questions on this. So this applies for both KP and also KC. So please take note of this. So overall, okay, these are the things that I have taught you, okay, related to this chapter until now. Yeah.